In this example problem, we'll work the titration of a weak base by a strong acid. We're titrating 50 milliliters of 0.15 molar ammonia with 0.1 molar hydrobromic acid. We want to calculate the pH after we've added 0, 25, 75, and 100 milliliters of hydrobromic acid solution. To calculate the pH before we've added any hydrobromic acid, we simply need to calculate the pH of a 0.15 molar ammonia solution. Since ammonia is a weak base, we can use a Rice table to calculate the concentration of hydroxide ions at equilibrium. For our initial concentration, we're starting with 0.15 molar ammonia. Since we don't have any product, we'll lose reactant and we'll produce product. And our equilibrium concentrations will be the initial concentration plus the change in concentration. If we write the expression for this equilibrium reaction, we'll get the Kb expression, where Kb equals the hydroxide concentration times the ammonium concentration divided by the concentration of ammonia, which will be equal to x times x divided by 0.15 minus x, and that's equal to our Kb value, which is 1.8 times 10 to the negative fifth. To solve for x, we can make a simplifying assumption. We can assume that 0.15 minus x is approximately equal to 0.15 because our Kb value, 1.8 times 10 to the negative fifth, is very small. So the expression becomes x squared divided by 0.15 equals 1.8 times 10 to the negative fifth. We can multiply both sides by 0.15 and then take the square root of both sides. And we'll get x equals 1.64 times 10 to the negative third. Since we made an assumption to simplify the problem, we'll need to check our assumption. We assumed that 0.15 minus x was approximately equal to 0.15. Our assumption is valid if our percent error is less than 5%. In calculating our percent error, we see it's 1.11%. So our assumption is valid. Now that we've calculated x, we know the hydroxide concentration at equilibrium. And using it, we can calculate the pOH. Our pOH is equal to the negative log of our hydroxide concentration, which ends up being 2.78. To calculate pH, it will be 14 minus pOH, which equals 11.2. So our pH of our solution, before we've added any hydrobromic acid, is 11.2. Next, we'll calculate the pH after 25 milliliters of 0.1 molar hydrobromic acid is added. To calculate the pH, we first want to know what region of the titration we're in. The three possibilities are that we could be before the equivalence point, at the equivalence point, or beyond the equivalence point. To determine what region we're in, we'll use a limiting reagent problem. We're adding a strong acid, so the strong acid will react completely with the weak base ammonia to produce ammonium and bromide. If hydrobromic acid is our limiting reagent, then we're in the first region. We've not yet reached our equivalence point. If we've added just enough hydrobromic acid to completely react with the ammonia, then we're at the equivalence point. Or, if ammonia is our limiting reactant, then we're beyond the equivalence point. Let's see which region we're in. First, we'll calculate the starting moles of hydrobromic acid. Our moles of hydrobromic acid will be the molarity times the liters of solution, which is 0.1 molar times 0.025 liters, or 0.0025 moles of hydrobromic acid. Next, we can calculate the moles of ammonia. So again, we take the molarity times the liters of solution, and we'll get 0.0075 moles of ammonia. We don't have any ammonium or bromide to begin with. To determine how many reactions each reactant can perform, we'll take the starting moles divided by the coefficient in the balanced chemical equation. So for hydrobromic acid, it will be 0.0025 moles divided by 1, which is the coefficient in the balanced chemical equation, which is 0.0025 reactions. For ammonia, we'll take 0.0075 moles divided by 1, which is the coefficient in the balanced chemical equation, and we'll get 0.0075 reactions. The limiting reactant is the one that can perform fewer reactions. So we know that hydrobromic acid is our limiting reagent, and will be in the first region of the titration, which is before the equivalence point. To calculate the change in moles, we'll multiply the number of reactions that the limiting reagent can perform, which in our case is 0.0025, times the coefficient in the balanced chemical equation for each species. So to calculate the change in moles for HBr, it will be 0.0025 times 1, which is the coefficient in the balanced chemical equation. And because it's a reactant, it should be negative. We'll do the same thing for ammonia. We'll take our 0.0025, which is the number of reactions our limiting reagent can perform, times 1, which is the coefficient for ammonia in the balanced chemical equation. And because it's a reactant, it should be negative. Likewise, we'll calculate the change in moles for ammonium and bromide ions. These are products, so the change is positive. To calculate our ending moles, we'll add the starting mole column with the change in moles column. For hydrobromic acid, that will be 0.0025 moles minus 0.0025 moles to be 0. For ammonia, it will be 0.0075 moles minus 0.0025 moles, which is 0.0050 moles. We can do the same thing for ammonium and bromide ions. Both of these will be equal to 0.0025 moles. If you look at our solution, we have ammonia, which is a weak base, and ammonium, which is its conjugate acid. So this solution will act like a buffer. And bromide, because it's the conjugate base of a strong acid, will not have an effect on the pH. So let's calculate the concentration of ammonia. It will be 0.005 moles divided by our volume, which is 25 milliliters of HBr and 50 milliliters of ammonia, for a total of 75 milliliters. So our concentration is 0.0667 molar. Our concentration of ammonium can be calculated similarly. We have 0.0025 moles of ammonium divided by our 75 milliliters of solution, so we have 0.0333 molar ammonium. Since we have a buffer solution, we'll use these values in the Henderson-Hasselbalch equation to calculate our pH. Since ammonia is a weak base, we can use this form of the equation. POH equals pKb plus the log of the conjugate acid concentration divided by the weak base concentration. To calculate pKb, it will be the negative log of our Kb value for ammonia, which is the negative log of 1.8 times 10 to the negative fifth, plus the log of our ammonium concentration divided by our ammonia concentration. So our pOH is 4.44. To calculate pH, we can take 14 minus our pOH, which is 9.56. So the pH of our solution, after we've added 25 milliliters of 0.1 molar hydrobromic acid, will be 9.56. Next, we can calculate the pH after we've added 75 milliliters of 0.1 molar hydrobromic acid. Again, the first step is to figure out what region of our titration we're in, and we do that using a limiting reagent problem. So we're adding our strong acid, hydrobromic acid, to our weak base, ammonia, to produce ammonium and bromide. To calculate the moles of hydrobromic acid, we'll take the molarity times the liters of solution again, and we'll come up with 0.0075 moles of hydrobromic acid. Similarly, we can calculate the moles of ammonia, and we find that it's 0.0075 moles of ammonia as well. And we have 0 moles of ammonium and 0 moles of bromide to begin with. To calculate the number of reactions we can perform with each of our reactants, we'll take the starting moles divided by the coefficient in the balanced chemical equation. So for hydrobromic acid, it's 0.0075 divided by 1, which is 0.0075. Similarly, we get 0.0075 for ammonia. This means that we've added just enough hydrobromic acid to completely react with our ammonia. So for our change in moles, we'll use the 0.0075 reactions times the coefficient in the balanced chemical equation. For hydrobromic acid, since it's a reactant, it will be negative 0.0075. Similarly, for ammonia, we'll have negative 0.0075. And for our two products, ammonium and bromide, we'll have plus 0.0075 moles. To calculate our ending moles, it will be our starting moles plus our change in moles. We'll have 0 moles of both hydrobromic acid and ammonia at the end. And for ammonium and bromide, we'll have 0.0075 moles. Since we added just enough hydrobromic acid to completely react with our ammonia, we're at the equivalence point. Let's look at our solution. We have ammonium, which is the conjugate acid of our weak base, and bromide, which is the conjugate base of our weak acid. Bromide will not have an effect on the pH. So the pH will depend on the ammonium concentration. So let's calculate the ammonium concentration. It will be 0.0075 moles divided by our total volume, which is 75 milliliters of hydrobromic acid and 50 milliliters of ammonia. So that will equal 0.060 molar ammonia. To calculate our pH, we can use a Rice table. Our reaction will be between ammonium and water to produce hydronium and ammonia. Our initial concentration of ammonium will be our 0.060 molar that we calculated. Our initial concentrations of hydronium and ammonia will be 0. Since we only have reactant right now, we'll convert reactant to product, so our change in concentration for ammonium will be negative, and our changes in concentration for hydronium and ammonia will be positive. Our equilibrium concentrations will be our initial concentration plus our change in concentration. Our expression is for Ka, so we'll calculate our Ka value. it's equal to Kw divided by Kb for ammonia. So that equals 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. So Ka for ammonium is 5.56 times 10 to the negative 10th. We can write the equilibrium expression for the reaction, and it's the concentration of ammonia times the concentration of hydronium ions divided by the concentration of ammonium ions, which will equal x times x divided by 0.06 minus x. To solve for x, we can make a simplifying assumption. We'll assume that 0.06 minus x is approximately equal to 0.06. So our expression simplifies to x squared divided by 0.06 equals 5.56 times 10 to the negative 10th. We can multiply both sides by 0.06 and then take the square root of both sides to solve for x. And x will equal 5.77 times 10 to the negative 6th. Since we made a simplifying assumption, we have to make sure that our assumption is valid. So we calculate the percent error and make sure that it's less than 5%. Our percent error calculation shows that we're at 0.00962%, which is well below 5. So our assumption is valid. To calculate the pH, we can take the negative log of the hydronium ion concentration, and our hydronium ion concentration is equal to our x. So that's the negative log of 5.77 times 10 to the negative 6th, which equals 5.24. So the pH of our solution at the equivalence point will be 5.24. In the last part of the problem, we'll calculate the pH after we've added 100 milliliters of 0.1 molar hydrobromic acid. Again, the first step is to figure out which region of the titration we're in. So we'll use a limiting reagent problem. We're adding a strong acid to a weak base, so our reaction goes to completion. To calculate the moles of hydrobromic acid, we'll take the molarity times the liters of solution. So we have 0.010 moles of hydrobromic acid. Similarly, we'll calculate the moles of ammonia, and we get 0.0075 moles. We'll have 0 moles of ammonium and bromide to begin with. To calculate the number of reactions we can perform with each of our reactants, we'll take the starting moles divided by the coefficient in the balanced chemical equation. For hydrobromic acid, that's 0.010 divided by 1. And for ammonia, that's 0.0075 divided by 1. So ammonia will be our limiting reactant because it can perform fewer reactions. To calculate the change in moles, we'll multiply the number of reactions that can be performed by our limiting reactant times the coefficient in the balanced chemical equation for each species. For hydrobromic acid, that's 0.0075 times 1, and because it's a reactant, the change is negative. Likewise for ammonia, it's 0.0075 times 1, and because ammonia is a reactant, the change is negative. Following the same process, we can calculate the change in moles for ammonium and bromide, and because these are products, our change will be positive. To calculate our ending moles, we'll add the starting moles plus the change in moles column. For hydrobromic acid, we'll have 0.01 minus 0.0075, which is 0.0025. For ammonia, we have 0.0075 minus 0.0075, which is 0, so we've used up all of our limiting reagent. For ammonium and bromide, we'll end up with 0.0075 moles. If we look at our solution, we have a very strong acid, hydrobromic acid, and we have a salt composed of ammonium, which is the conjugate acid of a weak base, and bromide, which is the conjugate base of our strong acid. The species that will have the greatest impact on our pH will be our strong acid, hydrobromic acid. So our concentration of hydronium ions will just be equal to the concentration of hydrobromic acid, which is our 0.0025 moles divided by our total volume, which is our 100 milliliters of hydrobromic acid plus our 50 milliliters of ammonia. So our hydronium ion concentration is 0.0167 molar. We can use this to calculate the pH by taking the negative log of our hydronium ion concentration, which will give us the pH of our solution, which is 1.78. So after 100 milliliters of 0.1 molar hydrobromic acid is added to our ammonia, the pH will be 1.78.